What is the largest star in the universe? Why is it so impossibly huge? And before we can answer that, what even is a star? Let's begin our journey, not to learn everything at once, just to get a sense of scale. The smallest things with star-like properties aren't stars at all. They're gas giants like Jupiter. Jupiter is 11 times wider and 317 times more massive than Earth. It's made of the same stuff as our Sun, just way less of it. The transition to a real star begins with brown dwarfs, failed stars. They have between 13 and 90 times the mass of Jupiter. But even 90 Jupiters smashed together isn't enough to ignite a true star. Brown dwarfs are glowy gas giants that don't fit neatly into any category. So let's move on to the real thing. Main sequence stars. Once a gas ball passes a certain mass threshold, its core gets hot and dense enough to fuse hydrogen into helium. That's a main sequence star. The more massive the star, the hotter and brighter it burns, and the shorter its life. The smallest real stars are red dwarfs, about 100 times Jupiter's mass. They're small, dim, and burn their fuel so slowly they can last for 10 trillion years, 1,000 times the current age of the universe. Barnard's star, one of our closest neighbors, is a red dwarf too faint to see without a telescope. Next are stars like our Sun. The Sun makes up 99.86% of all the mass in our solar system. It's 7 times more massive than Barnard's star, but that makes it nearly 300 times brighter and twice as hot. The Sun will live about 10 billion years. Let's go bigger. Small changes in mass create enormous changes in brightness. Sirius, the brightest star in our night sky, has twice the Sun's mass, but shines 25 times brighter. It'll last only 2.5 billion years. Stars with 10 times the Sun's mass, like those in the Beta Centauri system, have surface temperatures near 25,000 degrees Celsius and shine 20,000 times brighter than the Sun. They live just 20 million years. So is the formula simply more mass, larger star? Not exactly. The most massive star we know is R136a1, with 315 solar masses and nearly 9 million times the Sun's brightness. Yet it's barely 30 times the Sun's size. It's so extreme it loses 321,000 billion tons of material every second. Stars this massive are rare and short-lived. To make the biggest stars, we don't add more mass. We have to kill them. Red giants and hypergiants. When a star runs out of hydrogen in its core, the core contracts, gets hotter, and pushes the outer layers to swell enormously. Our own Sun will eventually swell to 200 times its current radius, swallowing the inner planets. But the true giants are hypergiants, the giant phase of the most massive stars. Their surface gravity is so weak they basically blow themselves apart. The Pistol star is 25 solar masses but 300 times the Sun's radius. Rho Cassiopeiae, a yellow hypergiant, is 40 solar masses, 500 times the Sun's radius, and 500,000 times brighter. If Earth orbited it at the same distance as the Sun, we'd be inside the star. And finally, the largest stars we know, red hypergiants. The current title holder is Stephenson 218. It probably started as a main sequence star a few tens of times the Sun's mass, but has since lost about half its mass. While typical red hypergiants are 1,500 times the Sun's radius, Stephenson 218 is estimated at 2,150 solar radii, shining with nearly 500,000 times the Sun's power. To grasp that scale, at light speed, it would take you 8.7 hours to travel around it once. The fastest plane on Earth would take 500 years. If you placed it where the Sun is, it would fill Saturn's orbit. Eventually, Stephenson 218 will shed more mass, shrink into a hotter phase, accumulate heavy elements in its core, and finally explode in a core collapse supernova, giving its gas back to the galaxy. That gas will form new stars of all sizes, starting the cycle of birth and death all over again. The universe is big. There are many large things in it. But even the largest star is just a temporary, brilliant chapter in a story that's been unfolding for billions of years.